Chapter 4 is the first one on simple random sampling, and also, like in later chapters, what we will do is we will define what we mean by the concept, and maybe especially in the case of simple random sampling, that has become clear. If you didn't already know that from before, of course, through preceding chapters, especially chapter 3. However, as we said before, in chapter 3, we still take the perspective that we can look from above at the population, take all possible samples, and then do calculations based on knowledge of all possible samples. In practice, we will have to work with a single sample. So how do we do that? Well, simple random sampling, as said before, the typical paradigm is we draw balls from an urn, we flip a coin, for example, for 0, 1s, etc. The quantities that we have to define it is, and this is just a repetition of chapter 3, the population, calligraphic P, the size of that population, survey time, for example, n is equal to 8. The sample size is what we choose it to be, and then from there we derive the sample fraction. That in itself is not fully defining it, but if we add either with or without, then it's fully defined. So there is only one way of looking at simple random sampling. If we have a population of size capital N, we draw samples of size lowercase n, and we do so without replacement. Then every possible application is exactly the same. The units may be wildly different. They may come from completely different scientific areas, but the sampling mechanism is identical. So just to give an idea, at the top line, in general, we say population size, sample size, okay. How many are there? How many possible samples are there? Well, n choose n if we sample without replacement. 6 units, of which we choose 2. That's 6 times 5 divided by 2 is 15. If we use numbers that we have been using before, A choose 2. For example, for survey time, that's 8 times 7, 56 divided by 2, 28, as we find here, etc. But if we sample without replacement, every unit can be, at every time, be sampled or not sampled. Then it's simply a power function. And that's the 16 that we saw before, for example, for the artificial population. It would amount to 64, more than double of sampling without replacement in survey time. And then in the Belgian Health Interview survey, there are 10 to the power 34,000 samples without replacement and 10 to the power 70,000 samples with replacement. Now, these are slightly rounded figures, but they're so astronomical, literally, that they're bigger, both of them, like the number of grains of dust, or atoms, if you wish, in the universe. So they're, for all practical purposes, infinitely large. However, with that in mind, so we see it quickly increases, and we can do enumeration and just list all the estimates, add them up, divide them by 28, for example. Yeah, we can still do that here. Forget about it in the Belgian Health Interview survey. We have to do something a little more sensible. Also, we talk about 6 and 16 in the artificial population, but didn't we say that some samples are actually sampled either in one order or another? Huh? Remember, 1, 2, and 2, 1, we really consider only one sample? Well, yes, and then the formula takes this form. It's like combinations with repetition, and so that's a factorial coefficient of the form n minus 1 plus n divided by n. Apply it for some of the examples, and you will see the number coming out. So, for example, in the artificial population, if n is equal to 2, the number of samples is n is equal to 4, capital N minus 1, plus lowercase n equal to 2, choose 2, which is 6 minus 1 is 5, choose 2. Well, 5 choose 2 is 10, as we find here. Okay, and that brings us to the end of chapter 4.